All right, welcome everyone to today's session on alert brokers. I'm going to go ahead and start right on time. We have a fairly full session, and so I want to make sure we have time to get through everything. So just the usual reminders to start. We have a code of conduct for the conference, which you've agreed to abide by, and you can report any concerns following the instructions there. Also, this talk is being recorded, so if you do not wish to be recorded, please keep your camera and microphone off. The videos will be posted tomorrow. We'll use Slack for questions, so feel free to navigate there to the channel for this session and post questions as you have them, and give a thumbs up to any that are particularly exciting, and we'll try to feed those back. Ken Herner is monitoring the Slack chat for us today. And finally, I'll note, again, in that Slack channel, there is a link to a live Google Doc, which you can contribute to the session notes if you like. So our agenda today, I'll start with an overview presentation from the Rubin project about the status of alerts and the alert brokers. And then we're going to hear from the broker teams themselves throughout the rest of the session and have, I hope, just a little time for Q&A at the end. But we'll need to keep it a little efficient, and so we're going to all present from one slide deck to minimize the transition times. So let me go ahead and begin. My name is Eric Bellum. I'm at the University of Washington, and I serve as the Alert Production Science Lead for Rubin Construction. And so one of my roles has been helping to shepherd the broker selection process through to completion, and I'm pleased to share those results with you today. So just to emphasize that the community alert brokers are really a key component of getting Rubin's real-time science out. So as Rubin surveys the night sky, every 39 seconds, it produces about 10,000 alerts for objects that have changed or appeared or moved. And we send those out to third-party alert brokers who are aggregating those alerts with a wide variety of other information from archives or from streams from other facilities at other wavelengths, and providing interfaces to allow scientists to identify events of interest, to trigger follow-up, to coordinate and communicate with each other. And so really these brokers are crucial for enabling that short time scale science that Rubin's wide, fast, deep survey is going to enable. The challenge, of course, is that there is a lot of Rubin data, and our design calls for very semantically rich alerts that have quite a lot of information in them. So there's a triggering difference image source, and as well as the associated sort of object or solar system object record, 12 months of history. So you have a light curve and you can see if there's past variation, as well as cutout images. And so when we package that all up, it's about 82 kilobytes per alert. And I've linked here throughout the slides to a variety of documents that provide more information if you're curious. And so we have to get these alerts out to the brokers within a 60-second time window from the completion of the readout on the summit. And so that implies relatively high bandwidth needs of about 5 Gbps for each full stream. And so we're limited in the number of full streams we can support by capacity from the data center. And so a year or two ago, we established a clear requirement to support at least 5 full streams to alert brokers. So the process has been two-stage one. We initially issued in 2019 a call for letters of intent for teams that might be interested in proposing to serve as community alert brokers. We got 15 letters of intent, as well as 3 sort of letters of non-intent, letters of interest supporting these ideas and other potential access mechanisms. We hosted a broker workshop in person in Seattle in 2019. And then invited all of those teams to submit full proposals. And the full proposal call came out in early 2020, and then we delayed the due date to December of 2020 due to COVID. and we received 9 teams. 9 teams submitted full proposals requesting full stream access to the alert stream. The proposals were reviewed by the Rubin Science Advisory Committee, or SAC, which selected its non-conflicted members and who were given the charge to recommend a selection of these brokers to Rubin using a set of evaluation criteria that we had previously outlined. And so the SAC recommendation came back that Rubin should support 7 brokers receiving the full stream from Rubin, and the additional 2 should be supported as downstream brokers. That's more than the required 5, so this is an expansion of scope, but the Rubin operations project consulted with our data facility, the US data facility at SLAC, and we believe that we can support both technically and with appropriate user support those full streams. So those 7 selected brokers are the Alerce broker in Chile, Ample in Germany, Antares and Babelmühl are both US brokers, Fink is in France, Lacer in the UK, and the Pitt Google broker again in the US. So we'll hear from each of these teams in a few moments. The 2 brokers which were recommended to serve as downstream brokers are Snaps and POI Variables, again, both US teams, and they are going to operate on streams forwarded from one of the full stream brokers. And I think that mode of building on top of these broker services that are being developed, I think is a really powerful idea. And I hope that they're the first of many new services that we see build up in this ecosystem. We're beginning to think about, now that we have that broker selection finalized, we're beginning to think about how we integrate those brokers into alert distribution. The first step is setting up MOUs with the broker teams. So that's more of a documentation activity, but we'll proceed with that shortly. We're kind of envisioning a staged approach to this integration. So prior to the proposal process, we had generated sample alerts in the expected formats from precursor data run through our pipelines. And made that available to both the broker teams and others who are interested. And so we expect to continue updating and improving those samples and making them correspond more and more closely to what we expect to go on Sky with when Rubin begins operations. We're also working on the alert distribution infrastructure, taking that from sort of proof of concept and testing to actually deploying in data facilities. And so as sort of an initial activity, we would expect to begin sort of connectivity tests where we take sort of sample alerts from precursor data and feed them through something like the production infrastructure to connect to the broker teams and provide an opportunity to send data out and test interfaces and so on, identify issues. And so that's probably going to be in the next calendar year. But again, sort of a low stakes way to get started. You heard a little bit in the commissioning session about the plans for commissioning ComCam and LSSTCam. The ComCam schedule is quite short and very focused on technical activities rather than survey. And I think that's going to conspire against us in terms of being able to commit to sort of real-time alerting with ComCam. But those ComCam data will be made available in the first data preview DP1. And so we will produce appropriate alerts at least by that time, and similarly use those for testing with the broker teams. And then in the LSSTCam commissioning period, that's when we aim to move towards more of a real-time alert distribution modality, especially during the science verification surveys. So that's the general idea, again, of sort of stepping our way slowly towards real-time alert distribution. And again, with these selection completed, we'd really encourage science users to explore the options for what the different brokers provide in terms of services. All of the brokers that proposed are using Zwicky transient facility data, which is active now and provides, I think, a useful preview for Rubin in terms of formats and science and so on. I just highlighted a couple of facilities of the various brokers that I have certainly explored and used as a scientist. And you know, as I think we're going to hear very shortly, there's a wide variety of capabilities at the different brokers, and it's worth starting to think about which ones are going to meet your needs as we approach Rubin operations. This slide, of course, we'll post after the session, just has some summary links. So if you want to dig deeper into the documentation, those links are here. So I will pause here and see if there are any questions that have come up on Slack. And Ken, if you're there and can read them.
I've not seen anything so far.
Okay. Pause for just a moment. Can do raise hand through Zoom if that's preferable. All right, well then we'll continue to the broker teams. So again, I will advance the slides. So just give me next slide warning. We're going through alphabetically, and so the first team is Alerce.
Hi, can you hear me?
Yep. Hi, Francisco. Go ahead.
Hello. Okay, so I'm going to speak on behalf of the Alerce broker. So it's the first slide, and just acknowledgement of all the institutions that are behind this project. It's many institutions in Chile, also in the US, and a big interdisciplinary team that you can see here. So it's been an amazing journey with the community, with other brokers as well, to start this new field. Next slide. I will first talk about some of the highlights of the project so far. So first, I have to say that we have been ingesting the alert stream from CDF since early 2019. We pioneered the classification using machine learning and a complex taxonomy that you can see here. Some key numbers of the project. So far, we have more than 2 billion non-detections in the database, more than 200 million detections. We have available more than 50 million classifications based on images, 1.5 million classifications based on light curves, more than 10,000 reports to the transient name server, of which 1,300 more or less have been spectroscopically classified. And also every object with at least six detection has 178 features available. All of these are available in real time, and you can access via front-end, Python client, API, or direct database connection. Next slide. More highlights, we have built a modular pipeline that runs in AWS, all in Docker containers. So all the steps of the pipeline are Dockerized, and you can scale them up using Kubernetes. We run 2 machine learning classifiers, one based on images that is made to provide real fast classification, and also one based on the light curves that provides a more complex taxonomy. And these are the confusion matrices associated to them. Next slide. Here you can see a video of the Alerce Explorer, where we have put a lot of effort designing. Here you can do queries, for example, query all the RLI stars. You can move between these objects very easily with the keyboard, look at the folded light curve, include CDF data release information, see the classification probabilities, image stamps, contextual information, cross matches. So it's really a lot of effort with the community developing this tool. Next slide. We really care about the user community, and for this reason, we have organized some workshops, one based on Alerce, and 2 others together with Think on the LSST Enabling Science broker workshop. And we have received a lot of feedback from the science collaborations. We have put many notebooks focused on specific science cases. I think this is very key to allow new people to start using brokers. And we have 76 videos available. We have a user community that is very broad, from 66 countries. And because of the early classifications that we submit to the transient name server, more than 1,300 objects have been spectroscopically classified. Next slide. Some of the new features that we are releasing is a new watchlist service. where you can actually submit a very simple list of targets, explore that, and wait for notifications. And also, if you can play the video again, we have integrated the CDF data release. And with this, we can look for outliers and look at the full light curve with data release, which is completely different to what you will see only with alerts. This allowed us to look for changing state again and do a systematic study of outlier detection algorithms. Next slide. We're preparing for Rubin with a lambda type of architecture with 3 layers: online processing, speed layer, offline processing, batch layer, and the serving layer that is where users connect to explore the data. But users can also connect to the output streams, to front-end APIs, Jupyter Hub, and power users can also connect directly to the database in the future. Next slide. So summary, some of the key numbers, our main tools, the Alerts Explorer to search and visualize objects, the Supernova Hunter to find recent supernova every day in real time, Jupyter Notebooks, which is the entrance point to start using the broker. We have made available the data release from CDF, which really allows you to do much interesting stuff like looking for outliers. We are enabling a watch list, and we have this architecture ready for Rubin. So you can find more information here, and thank you, and you're welcome to ask any questions if you're interested.
Thanks, Francisco. Maybe let's save questions for the end. Encourage folks to go ahead and post those in Slack. Since we're switching pretty rapidly here, I think maybe it'll make sense to batch those up at the end. So let's go next to Ample.
Hi, everyone. Jacob Norden. I'm going to describe the Ample project. Thanks. So I'll start by backtracking a little bit. I don't think I need to describe kind of the opportunities that we'll get through LSST. We'll get deep and accurate real-time data in kind of once in a generation kind. And at the same time, we'll have a range of other astronomical observatories that will be coming online. So we'll actually get reliable gravitational wave, neutrino, gamma ray detections. So looking ahead to the next decade, and with these upcoming observatories, the question we started from was whether we actually had the information processing tools required for the next decade. And we identified 3 major sources of problems that made it unlikely. The first being provenance. These surveys, or the observatories that are coming online, might be the kind of one-off legacy observations, such that we really want to make sure that we know what we did and what we didn't do with this combined data set. We won't be able to go back and redo the universe. The second aspect is complexity. We'll be looking at different data streams, and we will want to combine the information that we're getting from those, and we will want to do it as freely as possible. Anything else would be to ignore data that we're having. And already the easy task of combining different optical data streams is non-trivial, and looking at different kinds of messenger makes this just harder. And of course, there's the volume of data. The kind of tools or the ways to approach these problems that we would like to highlight and we think are necessary involves first being able to describe a full astronomical real-time transient analysis in a consistent single framework. So that sounds complex, and it is complex, but the reason you want to do it really has to do with provenance. Because every choice you're doing, from the first you look at data to your final table that you're publishing in the table, you will want to be able to revisit it and study the impact of those. And that then couples to the second aspect, being modularity. These new data streams will be so complex that we can't understand them all. So we need to have software modularity. We need to be able to plug in software modules developed by others. They need to be extendable, referenced, and they will surely develop during the LSST lifetime. So this requires a very thorough modularity, and then of course scalability. Whatever we build with those requirements needs to be scalable. So AMPL is a software framework that fulfills these criteria. So it's a modular and scalable platform with explicit provenance tracking. It's a public software that anyone can be running. You can see the link below. So next slide. So beside this, I'm just going to comment on kind of two structural properties of AMPL. And the first has to do with the tiers. So this is a broker session, and AMPL does incorporate a broker, but it's only one of the 4 tiers of AMPL, and in a lot of ways it's the simplest. The other tiers have to do with combining, enriching, and reacting to information. Combining might be allowing for complex combination of different data streams so that you can actually pick and choose between different data points of which ones belong together and construct states. The third layer then allows you to do calculations. So you can incorporate units that on some sort of states performs a calculation. This output of this calculation you can then store. And then in the final tier you can then do aggregate analysis on samples or reacting real time to interesting events. So what AMPL actually is a framework that allows information to pass through these different stages and execute units when they are requested and keep track on when a computation was being run based on what data and what the output was. And each kind of nuclear calculation is carried out by a unit, which is either requested from the AMPL shelf or especially written for a specific science program using domain knowledge. And most science programs then contain a mix of these. Next slide. And all of this comes together in an analysis schema. So this is a compact summary of which units an analysis requests based on what input data streams and using what parameters. So I'm not going to go through the pasted lines there, but you can see reference to the different tiers and you can see reference to different units. And each unit references a specific code block that is then being requested. And such an analysis schema can then be referenced, distributed, tested. It can be continuously developed by other groups, and it can be applied to real-time archived or simulated data. So in short, this is the kind of structure that we envision that legacy LSST real-time data studies can be run off. And kind of as a wish list for this community, it would be great to have a joint format for writing such analysis schema that can then be run on different broker infrastructures. Next slide. AMPL is of course developed by many people. You see some of the names here. If you want to have more information, there are different venues. You can explore the code. You can try it out using notebooks. You can read more about the structure in this reference, or you can just contact us. Thank you.
Thank you. All right, let's move on to Antares.
Okay, thanks, Eric. First, I want to thank Eric and the rest of the team at Rubin for putting this whole workshop together and the process that they enabled for us to put these broker teams together and go through this operation to select them. It's been really interesting and helpful, I think, for the teams to have this kind of organization with Rubin itself to make sure that things work properly as we go forward with the project. So I'm Tom Matheson. I'm at the Noir Lab, and here's a whole bunch of people who are working hard on the Antares time domain event broker. So the next slide, please. So just a brief overview. Antares is a broker, but I think that the key thing you should look at it is that it really is a time domain science platform. In other words, we view that its strengths are community driven, that what we have is a system where you can bring your own idea and implement it right now. If you have an algorithm for classification, if you can write that down as a filter, we can implement it today on ZTF alerts, and you can be getting a stream of those objects on your own machine right now. So we already have this capability of taking whatever you want to do and enabling it on the system where we've built the infrastructure that does the heavy lifting of processing all the alerts, keeping track of the large scale databases, and then providing you with what you want to do with the time domain science that you're interested in. If you want to know more about a lot of the details, the best thing to do is to go look at our website, because we don't really have time here to go talk about all the great things that Antares can do. So please go look at the website and you can play around with all the various tools that we have there. There's also a paper that came out earlier this year that has a lot more detail in terms of the technical description about how Antares works. The next slide, please. So what does Antares do? Well, when alerts come in, we annotate those alerts with information from external catalogs across a full range of multi-wavelength catalogs. Those alerts are then filtered. And like I said, those filters can be user defined. You can go to the data lab at Noir Lab and find a Jupyter notebook there, and it will explain exactly how to write your own filter. Even someone who writes Python code as poorly as I do can write a filter. So if I can do it, anybody can. We also provide a searchable archive of alerts. We have watch lists, so if you have a target that is of interest to you, we can let you know if anything ever triggers on it, and that notification goes out through a Slack channel, so you can make it as intrusive as you want. We have a web portal where you can look at the streams, the light curves, all the various things associated with those alerts themselves, and then those streams get output for whoever wants to subscribe to them. We track the provenance of how decisions are made. And we can enable direct integration with target and observation managers, and especially with the Astronomical Event Observation Network, EON, which is a joint collaboration between Noir Lab and Las Cumbres to build a large network of follow-up facilities that you can then trigger observations on across all of the available facilities that either Noir Lab or Las Cumbres or other facilities that end up joining the network. Next slide, please. So what are we doing right now? Well, like the other brokers you've seen, we're using a mature technology. It is all containerized with Kubernetes. We use Kafka for streaming. Our database systems use Cassandra and Elasticsearch right now, so this will enable us to scale up to LSST. Not only have we actually built something to play around with alerts, we're actually doing something with them. We're producing science, we've written papers, we're producing ATELs, we're putting things on TNS. So the thing that we have built right now, Antares, is already enabling the science we intended it to do using ZTF data. We're also enabling downstream science in the sense that, well, we are taking the solar system objects from the ZTF stream and redirecting that to the solar system team snaps that you'll hear more about later on today. But we're also working with the team at Purdue who built the refit tool to look at transient events and decide, well, what is the right, which are the ones that need to be followed up immediately. And they've built a large network of amateur astronomers to try to do this follow-up system. And so that's an example of how people can build systems downstream of the high-level broker operating on some small subset of it to do their own science. And that way you can operate on something that is really of interest just to you. And right now we're preparing to move to LSST scale. And we're doing that by, right now we're shifting our production system to the Google Cloud platform. We've already done a lot of tests there. In fact, we've done tests at scale. And we think that those tests have shown that we can take the technical solution we have and operate at LSST scale without any change to our overall design. So we believe we have a system that works now on ZTF. We have a system that can scale to the LSST rate and volume. So we are prepared to do that as soon as LSST starts to provide alerts at that scale. And finally, I just want to advertise that in addition to Antares, there's lots of other time domain science going on at the Noir Lab, and we're going to have a special session at the AAS this January to talk about all the things you can do with time domain astronomy at the Noir Lab, from your proposal through finding the alerts, through doing the follow-up, to all of the other things you can do for analysis with our data lab. So if you're interested in seeing this sort of complete end-to-end ecosystem, please come see us at that session. But if you have any other questions before then, like I said, look at our website or come talk to us or send questions through the Slack. Thanks.
Thanks, Tom. Let's turn to Babamul.
Okay, thanks, Eric. Next slide, please. So Babamul is probably the most unfamiliar broker to anyone who's sort of been following what Alessi, Antares, Sarah, and Fink have been doing, but is actually maybe the one which has got the most experience because we're coming from ZTF. So I'm Matthew Graham, I'm the project scientist for ZTF. And so as you have been hearing, all these other brokers are happily using our stuff to scale up and test. Next slide, please. But however, with Babamul, we've taken a very different approach architecturally from what's going on before. a lot of what has been done so far and thinking about brokering comes from ideas that have been in the community for at least 15, 20 years. First brokering meeting I remember was back in 2005 at NOAO, as it then was. And the sort of landscape I think we're existing in now is quite different from what was going on then. And we're thinking still about these very monolithic brokers. And the approach that we decided to take with Babamol is to actually go for a decentralized network of low-cost components. There's a whole thing called edge computing, which is how your smart car and your smart microwave and your smart fridge or whatever is working, where we have actually very powerful AI running on very low cost, low bandwidth commodities, and that this could form the basis of a broker. And so that's what we sought out to test and to develop. What Babamol is it's a decentralized network that we anticipate of these low cost components, plus an in-use science data platform for information management. So using the thing that we're already using in ZTF. And we estimate that any group could actually set up their own at-scale broker for less than $1 a day over the lifetime of LSST. Next slide, please, Eric. So this is actually working on demonstrated capability. These are not pie in the sky ideas. First of all, obviously with ZTF, we have, there are a number of brokers which are already using ZTF, as I've said, but we do have our own in-house system, which is this Fritz thing. It's open source. It's based around Josh Bloom's Sky Portal program. We're currently supporting 500,000 alerts a night, 200 users, millions of requests daily. We've got 50 terabytes of catalogs in there, 4 billion light curves, interfaces to robotic telescopes, all the things that all the brokers are commonly going to say they can do and whatever. So we have an information, a data management system already in hand, and it is easily scalable to LSST. LSST is really only 10 times the size of ZTF in terms of alerts and data volume. However, for our backend computing, we moved away from requiring supercomputers. You can do this with a Raspberry Pi and a commodity off-the-shelf TPU, which is a hardware accelerator specifically for deep learning models. And so what we have demonstrated is that on a Raspberry Pi plus one TPU, we can process a night's worth of ZTF alerts in under 3 minutes, which means that a night's worth of LSST alerts is processable for doing statistical inferencing on within 3 hours. And that's for $200. So imagine if you had, you spent $2,000 on those, you have 10 to 20 TPUs, each of which is dedicated to a specific inferencing model. You can classify the bejesus out of your alert stream as much as you want. So that is the hardware basis behind. And as I say, we have demonstrated this at scale with ZTF. Next slide, please, Eric. So the idea is that this is a fully open source, lightweight broker. And we will, the stuff will be being put out there so that groups who want to develop their own large scale broker but don't have the resources that they believe are necessary can actually do so. And we do this by continuing to build on ZTF and using ZTF as the test ground internally for what we're doing. So a transition that's happening that makes ZTF more LSST-like is that forced photometry is coming to the alert packets within the next few months. We are developing new models within ZTF, new data learning inferencing models that can be run at low scale on these edge TPUs. So we have a new one, SI, which will classify alerts into bogus hosted variable star nuclear orphan, can add more to that. One thing we're also doing is we're going to be doing an open model repository. So the whole idea is that instead of you having to train your own models, if other people have trained models on their data, they can put that in the repository. Then you setting up a low-cost broker, you don't need to do the development yourself. You can just pull those models out, maybe do some transfer learning if it's required, but it's all documented and curated. And so the idea is that that's what you would deploy, off the shelf. I want models 1, 4, 7. I've got 3 TPUs. I'm going to deploy them. That'll work on the alert stream. And finally, we're looking at federated learning as a way of improving some of those models. And that would be learning across some of these devices or maybe with some of the other brokers. And the idea there, I think you've slide dropped back, Yeah. With federated learning, you can do localized training of your model. So if you have proprietary access that you do not want to share, but you want to make use of that for your model, you can train your model up that way. Those propagate back to the global model that's in the model repository, and so everyone benefits from your proprietary data with data privacy. I think, yeah, and so that's where we are. So it's continuing development over the next year or so. We've got a couple of years yet before, but obviously as the UTF develops, as the LSST alerts are simulated and more come online from ComCam and such, you'll see more of these components beginning to appear. So thank you, Eric.
Thanks, Matthew. Let me encourage folks to go ahead and feel free to stage questions into the Slack chat as we go, so we can return to them in the Q&A at the end, or address them if folks want to comment there along the way. Next up is Fink.
Yes, thanks, Eric. That's very hard to convince you after this wave of TPU and futuristic things, but we are Fink, a monolithic broker developing tools to enable science for LSST. So we are based in France. So we'll shortly move to CCN to P3, which is also a satellite data processing center for LSST image data. So we are community driven. You can see at this link list of all the members of Fink and contributors, and we focus on several aspects of the stream. Our current research topics are listed at the bottom. So we started in 2019 on supernova and microlensing mainly. We're also developing ideas around active learning, using active learning for time domain data, and of course cross-matching the stream with already known catalog. In 2020, we had a solar system module and gamma ray burst as well, trying to cross-match or to, let's say, combine ZTF optical stream with GRB data. And this year we added 3 more modules, one focusing on anomaly detection, one on satellites and space debris, because we saw a lot actually every night, and one trying to basically find kilonovae, although we had none so far. Next slide. So here is the status. So since November 2019, we collect and process ZTF public alerts. By the way, we thank the ZTF team for providing the stream. That was very useful for the Fink team to develop and scale up since now. So since November 2019, we collected more than 100 million alerts. That's, well, a big database, but quite small for LSST, I would say 4 terabytes. Among those 100 million alerts, only, well, I would say 1/3 of those alerts were processed. This is just due to the quality cuts that we apply on the stream. So after we reject alerts based on their quality, they all pass through a series of modules and classifiers to try to get some labels on those alerts. About half of them are classified at the end of this process. And you can see at the bottom of this slide various categories on various labels after the processing. So we have catalog objects, and here you have literally more than 100 different labels from variable stars, pulsating, rotating, a lot of things. We have also solar system objects already known from the Minor Planet Center database. And then we have a range of candidates, so things we think could be interesting, so like supernova candidates, solar system candidates, or new candidates, and subcategories of supernova that can be interesting, like the 1A, type 1A, for example. We have also microlensing candidates and kilonova candidates. Next slide. So we do a lot of things. I just pick up some recent highlights that we are doing currently. So we're running a citizen science program focusing on kilonova follow-up. This is led by the GRANMA network of telescopes. So in Fink, we are selecting and distributing ZTF alerts to this network, and we are working with scientists, with amateurs, actually, that then follow up interesting candidates over the weekend, for example. We are also running a program on supernova type 1A follow-up. So each night we submit candidates to the transient name server for spectroscopic follow-up. And over the last 8 months, for example, we reported more than 600 objects. And among those 600, 395 were classified, with 316 supernova type 1a. So it's quite interesting to see those candidates finally classified. In Think, we, well, perhaps unlike other different teams, we had LSST requirements in mind from the beginning. So although we are using ZTF, we always wanted our system to be usable at the LSST era. And luckily, we managed to be selected. But that allows us from the beginning to develop and a lot of tools within the big data ecosystem. And especially we are working a lot, for example, on graph database for time domain science. So we think there is a huge potential for using graph to enable science with alerts. And we also focus a lot on building a broker ecosystem. So regularly make action with other broker teams. So Alerce mentioned the LSST broker workshop that we co-organized with them. That was a huge piece of information for us because we could interact with the community at large. We are also in Europe building collaborative European efforts with the MPOL and laser teams because we think if we are working together, that would benefit more to our different communities. Next slide. Last slide, how to access Think data. So we are collecting, processing the data, and then you as a user, you perhaps want to access this data. You have three ways. The first one is accessing the data live via the live stream service. You need authentication. It's very simple, but then you can access anything live. And you have two other ways. One is the Science Portal, which is a web application to explore all the Think aggregate data. There is a link. I promise I will buy a domain name one day, but for the moment you have to use the IP address. And there is a REST API available. So there is a web service and the REST API. And the last thing is to using the Tom toolkit. So we made a module for Think. Well, behind it's just using the API, but it's quite convenient if you're already using Tom for your work. Next and last slide. Feel free to contact us. We are community driven. So basically your science can be incorporated in Think. We would be happy to provide services. There is everything to contact us. Don't be afraid to be creative. Thanks.
Thanks, Julian. Let's move on to Lasser.
Hello, my name is Ken Smith. I'm presenting for the Lasser broker. Just want to say thank you to the team for selecting us and for showing us confidence, and hopefully we can reward that. If you're wondering what Lasser means, it's Irish or Scottish Gaelic for flash or flame. It doesn't actually stand for anything, although you can make it if you want. It's a UK operation, but primarily our teams are based in Edinburgh and Belfast, hence the Irish-Scottish connection. So the links on this page basically link you to what we're calling the legacy Lasser broker and our current development broker. We have another one in the process of being developed, and eventually all these links will merge eventually back to presumably Lasser. But anyway, that's what the links are for. If you want to know more, just have a look at that quick research note. Although the screenshots, etc., are becoming increasingly out of date as we develop the software. So next slide, please. So this is just a cartoon overview. I don't really have time to go through it. The only thing I want to mention about this is really that we've been operating since 2017 with the Zwicky transit facility. We have in our system 190 million alerts, slight difference in the numbers between the different brokers. I must have a discussion about that. We are being actively scientifically exploited. Other people are using our broker to triage objects for follow-up, in particular, for example, for the ePistol Plus survey, which follows up transient down at the New Technology Telescope in Chile. So it's actively being exploited. We made a decision just not directly to report objects to TNS. Other people are doing it via Lasser. We are not doing it at the moment just because there's that human screening element that needs to be in place. We're not quite at the automated stage of getting everything completely, totally automated to go to the TNS. And I don't believe at the moment we have the current bandwidth to deal with that. But that's why we're taking that approach. So just the right-hand side of the screen just shows how users will interact with it. Just a quick word about Kafka, which is the queuing system, the preferred queuing system that the Rubin Observatory are using to distribute the alerts. We're using it to consume them. We're using it to transmit the data through our pipelines. And we're using it to emit data to customers if they want it that way as well, and on the user side of things. So next slide, please. So what is LASER? So it's, you could say it's an LSST alert stream annotator, interrogation and reporting tool, if you want to start using acronyms. You can define your own user-defined alerts using SQL or an SQL-like language. So a query can become a filter. You can save that query, which becomes a stream that you can outjust as a topic to one of the Kafka topics. Although you can receive the data in different ways other than Kafka, if you really want. Other brokers have, of course, mentioned watch lists, your favorite list of things you want to keep an eye on. And you can, we obviously do, we're able to do massive cross-matching at the moment up to 1 million positions. And then to attach triggers to those things, you know, has the thing brightened by, you know, n magnitudes, etc. So you can keep an eye on watch lists. We curate the light curves. Of course, we only get 12 months of data with the input alert, but we will keep beyond 12 months in our databases. So we annotate by context. This is a separate piece of software called Short, which Dave Young has developed, and that is based on locally ingested Sky catalogs. And Dave has also developed a piece of software as well that allows us to keep track of the probability contours for things like gravitational wave alerts or even neutrino alerts, so that we can keep track of objects that lie within those probability contours and tag them for follow-up. You can interact, as with the other brokers, with the system via our Jupyter notebooks and an API, which takes me to the next slide. Next slide, please. Yeah. So we've just made available a REST API. So follow those links if you want to know about which services are available. So our Jupyter notebooks were developed, but we moved them to Google Colab as part of our workshop that was very well organized by our Chilean colleagues in April, our broker workshop. So our Jupyter notebooks are hosted there currently. The system is currently deployed, automated with Ansible and Docker and the various tools for kind of wrangling those systems. Yes, our UK cloud infrastructure is undergoing a large upgrade at the moment, in particular making available a lot more SSD than we currently have. The network bandwidth is increasing, and that's actually happening next month, the process of that upgrade. So of course we can now automatically deploy the entire platform, not just new nodes with our setup. So we're working with other people and indeed other brokers to integrate user-provided classifiers so that we can, for example, work with other brokers that have maybe algorithms that we don't have internally, and be able to present a way of them receiving a stream and then feeding that data back to us, that we can annotate that data so that someone else can subsequently consume. So we're currently looking at integrating that. So our public Kafka stream, I've talked about Kafka, the queuing system, is now available at that address, kafka.lsst.ac.uk. And then the back end, so I talked at the beginning that we've got 200 million or so detections in the database. Of course, that's only 20 days worth of LSST data. and we've been collecting that over 4 years. So it's a really big scale up. We're used to working at that scale because of our work with Pan-STARRS and Atlas, where we dealt with a lot of detections, although most of them were junk, from chip problems and things like that, which is being dealt with upstream in terms of this project. So we've got a NoSQL and relational database type blend as our backends, and we're making that scalable. I've already tested at scale with Atlas, with 30 billion or so detections from Atlas, which is basically the total number of detections we'll get over the 10 years. So we're building hooks on it to enable solar systems science. So for example, I mentioned above that everything is spatially indexed. So they should be able to look in the database for objects at this position at this time. We encourage, I'm working with Meg Schwarm, of course, to exploit that. And then we are transitioning as well from ZTF, the current ZTF schema, out to LSST, of course. So that's coming soon. And we're hosting next month a kind of countrywide UK-based external user review. That's happening next month. That's all I've got to say.
Thanks, Ken. Final full stream broker is Pit Google. Apologize, we're pushing towards the end of the hour, so let's forge ahead. And thanks everyone for keeping as tight to time as they can.
Hi, thank you. My name is Troy Rain. I'm a grad student at the University of Pittsburgh. I'll be giving this presentation on behalf of our group, including our project lead, Michael Woodbasey, Ross Thompson, Christine Mazzola-Daher, and Daniel Parafort. We are building a broker on Google Cloud Platform, or GCP. That's the only acronym I'll define for you, but I'll use it quite a bit. Getting the data on GCP opens it up to access through the use of Google's APIs, which are mature and well-documented tools for accessing the cloud services like PubSub and BigQuery, which house the data. It also gives you the option of working next to the data. You can take advantage of GCP's cloud computing services. Our broker is in a relatively early development stage compared to the other full stream brokers you've heard from so far. But we are currently running the ZTF stream, and we're planning to run the full LSST stream. I will talk about the data and how to access it for the next couple of slides. You can access everything in Python or from the command line and many other methods. Next slide. Thank you. I want to show you just a little bit about how our broker software works to help explain the data coming out of it. This is a diagram of our software model. There's a few main components. On the left, the database storage component sends the data to BigQuery tables. BigQuery is designed for scalable analysis over petabytes of data. So that's great for LSST. So you can query those using standard SQL. The file storage component stores the full alert packets in a public cloud storage bucket, and you can download them from there. On the right are the processing and value added components. This is in active development, and we're still putting the pieces in place. Here I'm just showing a more high-level view of what you can expect. I'm not showing individual connections in the pipeline, but for example, the classifiers box represents multiple classifiers that may be connected to one or more filters and cross-match input. The thing that I really want to point out with this is all of these blue PubSub streams. PubSub is an asynchronous publish-subscribe messaging service. Most people in this group are probably more familiar with Kafka, which has a similar function. The first thing that our broker actually does as a Kafka stream comes in from a survey like LSST at the top is to republish it as a PubSub stream. That full alert stream is immediately available to the public. The other components of our broker actually get the data by listening to that stream. As the alerts make their way through the broker, a PubSub stream is published at every step. So for example, each filter and classifier publishes a dedicated stream. This is a core part of our data model. It allows you to hook into the pipeline at any stage. So you can get anything from the full stream to lightly filtered streams or fully processed and curated streams. Next slide. So that's a bit about the data and formats. With my last 2 slides, I'll talk about how to actually access it. There is a one-time setup that is 3 steps. You need a free GCP project of your own. Then you set up an authentication key. Then install the Python API or whatever tools or languages you want to use. These steps are very similar to what you would do to connect to other brokers. The difference here is that since the data lives on GCP, you get your account and authentication through GCP rather than through our broker. Next slide. After the one-time setup, you can query the databases, download files, or listen to message streams. There are links in our documentation to all the Google API methods and languages that are available to you. And then we demonstrate Python and command line methods. So here I'm showing one example of using Python to listen to a pub/sub stream. We've written a package, PGB utils, that contains thin wrappers for Google's Python API. These are working examples, and you can use them as is, or you can look at the source code to see the actual Google API calls. In this one, there's less than 10 lines of code in there to make the actual pull request, unpack, and acknowledge the message. And then we put in a few more lines of code to wrap some options. The PGB utils package and our tutorials in general are designed to let you do the most common tasks with just a couple of lines of code, and to give those who are interested in going deeper a good start on learning how to use Google's access tools themselves by looking at the underlying source code or following the documentation. Thank you.
Thanks, Troy. All right, let's move to the 2 downstream brokers. Nina here for POI variables.
Hello, everyone. So my name is Nina Janicek, and I'm the lead developer of the point of interest variable store alert broker. Our motivation for the broker was observing variable stores and especially doing spectroscopy of variable stores where we need accurate and very recent photometric light curves to get correct periods and phases. It's especially important as many periodic variable stores actually show a modulation of phase and period. So relying on older light curves is problematic when you want to time your spectroscopic observations to specific phases. So this is the background where we started out, and users should then be able to generate their point or regions of interest, which can be predefined, something like known stellar streams, dwarf galaxies, globular clusters, or they could be absolutely user created, something like a subset of a stellar stream. Next slide, please. As an output, users will get the light curves, so we will keep them beyond the 12 months. And of course, we will provide value-added information such as cross-match with external catalogs and our own calculated periods, phase offsets, then other more specific features that will be used in classification. So we will provide the features both on their own to the community, and we will also use them for classification. And this, as I said briefly, will be especially interesting for astronomers working with variable stars and who are interested in doing their own follow-up observations based on light curves. Next slide, please. Currently, we're processing ZDF alerts as all the other brokers are also doing. Here you see on a screenshot of our website, which is not publicly available yet, but will become available in a few months. And what users will get from us are classification results and features, as well as an overview of the light curves. And those will be available from the website, so users can create accounts, will be available from email and likely also via an API. Next slide. So as a summary, this is a lightweight broker for variable stores, and it will become shortly a downstream broker for Antares. And we think it's especially important to have such a broker, as LSST will enable us to get accurate and precise light curves for a much larger sample of objects, as this was the case for previous surveys such as Penn stars. And we think from our experience with spectroscopy for variable stars such as Larry, that it's extremely important to have accurate and up-to-date light curves.
Thank you, Nina. We're at the top of the hour. The next session will start in 15 minutes. We'll go ahead and conclude with the Snaps broker and maybe a question or two, but if folks need to drop off, of course, feel free. Snaps.
Thanks, Eric. Thanks, everybody. I'm David Trilling. I'm the PI of Snaps, which is the Solar System Notification Alert Processing System. We are a downstream broker, which means we're listening to an Antares rebroadcast of only solar system objects. And so it's a very small subset of the entire alert stream, of course. And like everybody else, we're listening to ZTF presently and preparing for LSST. And you can see at the bottom here that the main thing we're doing is deriving physical properties like colors, light curves, activity, and so on for solar system objects. Next slide, Eric. Thank you. Here's very briefly our architecture on the right side. I'm showing that our database can listen either directly to an alert stream, or in this case, we're listening to a rebroadcast from Antares. We are ingesting adjacent databases into our database. We have a real-time processing, like as soon as an alert is received, we do some analysis, and we also have a daytime processing, which is comparison within an ensemble, looking for outliers. So on the left here, it says we identify real-time outliers. We can also identify population outliers. That's our daytime processing. And we've pushed a synthetic population through the whole architecture. Next slide. Thank you. Oh, it's a little bit cut off here, but one thing that we've done actually only in the last few weeks is we're now have attached two telescopes to this outlier detection scheme. On the left side is the Lowell Discovery Telescope, 4.3 meter. It's about an hour that way. And on the right side of that is a 1 meter Q facility, also operated by Lowell Observatory, that we have access to. And so we're routinely now shipping interesting objects to these facilities. Okay, next slide. Thank you. So here's just an update of our current status. Our database as of a week ago is something like 10 million observations and 360,000 unique objects. Again, these are solar system objects only that we're talking about. We are carrying out real-time and daytime processing. We have some dedicated compute resources. Our web interface, we do have one. It's an alpha version. It's not available to the public yet, sorry, but we're getting there. We do have this manual telescope follow-up that I just mentioned. And what that means is that I look at targets and we ship them to a telescope. And we are at the moment, partially funded by NSF and LSSTC. And Eric, the last time step, please. Thank you. Over the next 12 months, here's where we're going. Of course, we'll continue to ingest ZTF data. We're going to push this full-scale synthetic LSST data, which is the Solar System Products Database, is maybe what that stands for, again, through our entire processing, and that will allow us to test at LSST scale. There will be a public web interface, probably the beta version. The telescope follow-up will be transferred from manual to robotic. Of course, we'll be writing additional funding proposals. We'll be generating our own alert stream of these candidate interesting objects that will be coming alpha version in the next 12 months, and an API as well. Thank you.
Thanks, David, and thanks to all of the broker teams for those exciting presentations. It's always fun to see what's coming out. We again are over time, so if you need to take a break before the next session, which starts at 12 minutes, please do so. I'm going to grab just a couple. There's lots of good questions in the Slack channel, which I encourage you to take a look at. I'm going to pull maybe just a couple here for a couple minutes. Josh Bloom asked if each broker has its own pathway to filter the same alert. Is there some project plan to run a bake-off for comparisons? I would say that's not something the Rubin project is planning ourselves to coordinate right now. But I think that's something certainly I think it would be very interesting. And so that might be something that we could develop sort of from the community side a little more organically, either with ZTF data, or I saw Gautam mentioned plastic, which is an excellent choice, and set us up as we move into the Rubin era. There's an interesting question about cross-matching that is a fairly technical one. Let me maybe end with Michael Strauss's question to all the brokers about how users should think about their choices and how brokers are thinking of synergizing or not now that we're sort of past the selection process and into the building for a decade-long survey process. So I don't know if any broker representatives want to take a stab at that one. Feel free to unmute and jump in.
So the Think team and the Ample team have already mentioned that we, in the European side of things, have already started discussions about doing some kind of synergy. So mostly the different brokers have different algorithms for doing different things. And is there a way we can easily integrate it into the stream that goes out from our broker, the results from another one? So that's the kind of thing that we've been discussing at the moment, and we're looking at an implementation, or we're testing an implementation at the moment. So I don't know if that answers many questions or raises many more.
Maybe both, but I think it's definitely germane. Thank you, Ken.
Mm-hmm.
Other comments folks want to give to this question?
So Eric?
Yes, go ahead, Francisco.
So perhaps, yeah, I put a link to the workshop that was mentioned during the talks. I think this was a very interesting experience. I mean, we're exploring different solutions, and I think this is very good. And we're to some degree converging, but also in some ways we're not. There are different visions. For example, what is a broker a filter system or a classification system? I think it's good to have these different visions. So I will just keep the diversity in the brokers.
I would tend to agree with that. Any other comments folks want to raise in response to this question?
So maybe one quick comment might be that if you should maybe not start thinking about what comparing the brokers, but rather start thinking about what real-time LST science do you want to do, and specify the requirements for that, and then see if that can be done on one or more of the brokers. So I would start with formulating a science problem and then see, can this be done? Great. Can this be done now? Really good. Do we need to do some development to make it happen?
Yeah, I think that's great advice. Thanks. All right, well, let me close the session here because we're over time. Welcome you to respond to more questions on Slack or ask more there. Thank you everyone for your participation, and may see some of you in 10 minutes in the time series feature session. Thanks everyone, bye.
Thank you.
Thank you, bye.